Hi, this is David Davis, and I'm here with John Dickinson from swiftstack. How you doing, John?
I'm doing great. Thanks for having me.
Great. So I've been learning about swiftstack from you and the Swift Object Store, and it's really fascinating stuff. I wanted to talk a little bit more about some innovations in storage technology.
Okay.
And one in particular that you were telling me about is, I'm picturing a hard drive with an Ethernet connection, and I just plug into it. I mean, I've seen, there's little like pocket NASs and stuff.
Sure.
So, I mean, what does this do, and how is it different from that?
Yeah. So one of the cool things about Swift is that it essentially abstracts away your storage volumes. So you can have a lot of opportunity for both open and proprietary vendor-specific innovation on that layer of the storage system. So one of the places that we've seen this happening so far is with Seagate. And last November, they announced their Seagate Kinetic platform. So the impetus behind the Seagate Kinetic platform is to reimagine what a hard drive could do if you actually started from scratch today. And one of the things that they've been able to do is say that, let's take the same form factor of the plug, but let's redefine the way the pins talk on that and just make it a network connected device. So you don't have to go through the traditional I/O buses on the motherboard. You don't have to go through SATA connectors or SAS connectors or things like that, but rather I can literally plug this directly into a switch backplane in a box and then upload that to my top-of-rack switch, uplink that to my top-of-rack switch, and literally, let's ping my hard drive. And you can trace route to the boot record. It's crazy stuff.
Wow.
But the really cool thing and the opportunity for innovation there is that you're eliminating a lot of those intermediate abstraction layers between the storage application and the actual storage media. So what we've been working with Seagate on, and we demoed last November at the OpenStack Summit in Hong Kong, is OpenStack Swift running on top of Seagate Kinetic drives. And the really great thing about this is now the actual storage media can communicate very effectively with the storage application itself. And there's a lot of really good efficiency that can be done there. So the storage application can hint a lot about the data that is being stored so that the hard drive can actually make a lot of efficient decisions on how to store it. And then conversely, the hard drive itself can report at a much more application-specific level what kind of data is bad, what kind of data is good, and how can we efficiently communicate that back so that the cluster storage system, Swift, can recover from from particular failures more gracefully, and you can get a lot lower mean time to detection and mean time to recovery of your failures running on this. So the really great opportunity here is looking at and hoping that this is going to become much more pervasive throughout the industry so that you can have new sorts of devices that are able to allow you to have a lot lower TCO for your storage system and a lot more efficiency in your storage applications.
Wow. So, I mean, with the hard drive, it's not talking NFS or iSCSI.
Not at all.
Okay.
Speaking Ethernet, actually.
Speaking Ethernet.
Yeah.
Wow. So you've got swiftstack on top, and you're storing objects,
right?
Which we talked about in our other segment here. Objects could be really, just about anything you see on the web.
Right.
It could be Dropbox. It could be just a general
file.
File
Documents,
video,
images,
file.
videos,
right,
all of that,
okay.
yes.
And that's being pushed directly from Swift right to the hard drive.
Right.
So some of the things that are illuminated in that, why don't you tell us?
Well, there's a lot of things. When you think about a storage system or really just anything running on a standard Linux server, before the data actually gets to the hardware, the actual physical geometry of the drive, it goes through a lot of layers. You've got probably your libraries that are talking to, originally talking to the file system, which goes through several Linux kernel translation layers, up to and including, all the way getting down to the I/O buses and potentially talking through RAID cards, which may reorder things or redo things. The firmware on the drive itself. And so by eliminating all of that so that the application can simply have a library that says, here's a key, here's the data associated with that, go store it, and talk directly to the drive, even if the drive isn't necessarily directly connected to that server. Becomes really interesting. It allows you to potentially get very, very dense storage systems and multi-home your drives, talk to them at the same time.
Wow.
I'm really excited to see where we can take this,
Yeah.
but the idea, the kernel of what we've got today is really exciting.
So the drive can even start to predict. It knows if this first bit of a file
Exactly.
comes, it's going to expect the rest of it.
Right. So one of the things that's really great about the efficiency of the storage media knowing about the storage application and vice versa is that if a library, if Swift says, here's a key, I'm going to store some data with this, now the drive actually knows that if I'm starting to see access on a particular value, it knows that data is going to be generally read from all of it or written to all of it, so that it can then store that much more effectively, very particularly to that drive's geometry, and make efficient storage decisions. And likewise, what's really great is if something happens actually on a physical surface of a drive that affected some value, the drive itself could report back up, these keys are in danger of data loss or something like this, and it can report it back up to the storage system, which then can say, okay, well, you can rebuild that or correct it from a fresh copy someplace else within the cluster.
Yeah.
And dealing with literally hundreds or thousands of these plugged into one storage system, then you've got a lot of efficiency in your storage that you can go about.
So right now, if I've got a bad block on a traditional
Right.
hard drive, how does the file system know what file is affected?
Normally you don't until you try to read that file, and then you read partially into that file, and then you get some problems, and oops, you've got problems. At some point there may be some scrubbing that's going on in the background that detects that for you, but it's an extremely expensive operation today to say that a particular sector on a drive is bad. Let's do some sort of inode inversion in the file system to figure out what actual files exposed to the user are affected. And it's just an incredibly expensive and painful. Generally, you can't do it at scale. So being able to have the drive itself report back, here's the logical files or objects that are actually at risk, becomes very useful and very helpful. And it's a really exciting innovation, I think.
Yeah. Well, I appreciate your time today telling us about some exciting innovations, in storage. Where could I go to learn more about Seagate Kinetics and SwiftStack?
Clearly, the great place to look for Seagate would be Seagate's website.
Okay.
You can go find their Kinetic stuff there. With SwiftStack, definitely check out swiftstack.com, and you can find some references there. But we've got our implementation, our adapter layer for the Seagate Kinetic drives available on our GitHub account, open source, github.com/SwiftStack, and you'll find our Seagate Kinetic interaction there.
Awesome. Thanks so much, John.
Great, thank you very much.